Swayam Prabha. Digital India. Educated India.
Morning, everyone. What I want to try to cover is first talk about elasticity. And since, again, I don't know where you start from, so I decided to start from scratch, but then I'll have to make some giant leaps at some point to cover everything. I mean, to talk about the basics in an hour and a half. So we'll see. If I go too fast, just, ask questions, stop me, and then we'll take the time needed for you to follow what I'm saying. So I'm going to quickly talk about stresses and strains, Hooke's law, and then mechanical equilibrium. And I've put up here some of the references some of the books that I really like. So the Landau and Lifshitz theory of elasticity is great, mathematically involved, but great. This one by Timoshenko is a bit more accessible. And then these two, we're going to talk more about them in the next lecture on elasticity. Okay, we'll try to do elasticity together. So what I like to, so in elasticity or in mechanical, for mechanical properties in general, the reference test is always it's the tensile test. So I'm sure you all know the idea is that I have, for example, a rod here with a surface S. It's glued on one side to a fixed structure, and then on the other side, I apply a force F. And if I'm pulling on the rod, so the rod has an initial length L, and due to the force that I apply, the rod will extend by some length delta L, right? So fine so far. Now, the idea is that imagine that I have a rod of, say, 50 centimeters, and then it expands by, say, 1 centimeter. If I take a rod which is now twice that length, if it's 100 centimeters instead of 50, delta L will be, what will happen? It will be twice bigger. So if I want to remove that basic size effect, what I want to look at is not the extension by itself, but it's the relative extension. So it's delta L over L, and this is the strain, the tensile strain, right? Same thing. In that experiment, the force itself is not the quantity that I'm interested in. What do I want to plot? If I want to remove size effects, the stress, which is what? The force divided by the surface, right? Clear for everyone too? So this is the stress or the tensile stress. And now I need a relation between what I apply. So I apply here a force, so I apply a stress. So I apply a stress, and in response to that applied stress, I have a strain. Now I need a relation between both. And what is the relation? So it's going to be Hooke's law, which says that the stress is, so it's directly proportional to the strain, and in between I have the Young's modulus, right? So this is Hooke's law. And this is Young's modulus. In terms of units, what are the units of stress? These are pascals. So it's Newton per meter square, right? And so the units of Young's modulus? Same, right? Because strain has no unit since it's metered over meter. So here, the Young's modulus is in pascals. Right, so, and this initially, so this Hooke's law was proposed by this guy, Hooke, and he did everything in analogy with springs. So he said, With a spring, I apply a force F and I have a displacement X. And so the equivalent of the force was the stress. The equivalent of the displacement was the strain. And he said, like with a spring, that the force is proportional to the displacement with the spring constant in one case or Young's modulus here. Same analogy, if I ask you what is the elastic energy which is stored in the rod once I have pulled on it, what is it going to be? So the elastic energy. So it's going to, so we have, I always, so let's put U, or no, it's, I can put free energy F. I know because there's F here. Let's call it U. So it's going to be like with a spring, it's 1/2 of the force times the displacement. So here it's 1/2 of the stress times the strain. And using Hooke's law, this is also 1/2 of Young's modulus times the strain squared, or it is also 1/2 of the stress squared divided by Young's modulus, right? What is the unit of that energy here? So it's Newton per meter squared. So this is not an energy. Yeah. So we need to multiply by a volume. So actually, this is a density of energy. So to have the energy, actually, what we have to do is multiply by the volume everywhere, with V being the reference volume of the rod. So everything is fine here? Yes? Okay, this is for a tensile stress. Now we can apply other types of deformation. Give me another example of shear, for example. So if I do shear, what's going to happen? So if I have a sample like this, what do I do to apply a shear? So now, so I'm going to start to put axes. So this would be X, this is Y. So to have a shear, I apply a force like this. So it's a force along X. And the result will be that the sample will be sheared like this. So it's going to take this shape, for example. And so I have a displacement which is here. And the displacement is along X, so I'm going to call it delta L X. And now I can call, so this height here is along Y, so I'm going to call it Ly. And then I have a length here, which is Lx. And then there's also along the Z direction. For now, we don't really care about it. What is the strain? So that was a bit fast for me. So say it louder. So it's delta Lx. You sure? It's not divided by Lx? It's clear for everyone that if I want, again, yeah, if I want to remove the size effect, I need to divide delta Lx by Ly and not by Lx, right? So delta Lx over Ly. And what is the stress? Yeah, but the definition of the stress with respect to the force, this is, so it's Fx divided by, so by the surface on which I apply it, and that will be Lx times the Lz we haven't talked about, right? So Lx divided by Lz. And then the relation between the two is the stress, which is G times the strain, and G is the shear modulus. Another type of deformation? What other deformation can I apply? Pressure, right? So we can look at pressure also. So what is a pressure? yeah, it's the same stress on all sides, right? So I have my sample, and then I have a stress on, I need to apply the same stress in all direction. And so that stress usually, for a pressure, we call it P. So we have P in all directions, right? So P is so it's the force that I apply divided by the surface. But now we used to say, so here in that example, if I apply a positive stress, I'm pulling on the system. For pressure, if I apply a positive pressure, I'm compressing. So here, we always have to be careful that there's a minus here. There's a convention with a minus compared to the definition of the stress here, right? So I apply a pressure. What is the corresponding strain? It's a volumetric strain, right? And so it's I have a volumetric strain, which will be the variation of the volume divided by the original one, by the volume itself, right? And the relation between the two, it's the bulk modulus. And I have P, which is, there's the minus because of this guy. There's a minus B bulk modulus delta V over V, and this is the bulk modulus. It's clear for everyone. There's a last one, which we haven't talked about yet. And actually, it's related to this deformation here. There's one aspect we haven't talked about. If I'm pulling in that direction, usually because every solid, so no solid is exactly incompressible, but they are all a bit incompressible. And so if I'm pulling in that direction, the system will tend to, or most systems will tend to shrink in that direction to try to keep the volume constant. And this is shear, this is pressure. And I think I'm not gonna put it on the board because it's not that important, but so we've covered all this. And so the last we haven't talked about is this compression. So if I'm pulling here, the system will tend to contract. And the contraction, so the ratio between the contraction in the x direction compared to the extension in the y direction is a Poisson ratio, nu here, right? Which for most materials is positive, but it doesn't need to be. It can be negative. And what kind of material, what's the name of the materials that have a negative Poisson ratio? It's the oxidic materials, right? So in the oxidic materials have this weird property of I'm pulling here, and instead of contracting, it's going to expand laterally, right? And then we have the bulk modulus. Now here on purpose, so here I haven't done it yet, but I'm going to do it here. We can start to put indices. So here, for example, this gamma here, it relates an extension in x with a length in y. So I have a gamma, I can write a gamma x, y. For tau here, I have a force along x, and it's applied. So here we have put the surface here, Lx times Lz, but more generally, actually, what I'm doing is I'm applying a force here on a surface which is perpendicular to the y-axis. So, or Ey, a unit vector in the y direction. And so here what I'm going to go, and what I'm going to call it is I'm going to call it tau of x, because it's a force in x, but it's applied on a surface perpendicular to y, so it's a tau x, y. Here, for example, if I put axis here, same axis, x and y, this epsilon, what would be the indices that I would use for epsilon? I would do, for epsilon, I would do y. Thank you. Yeah, because it's a delta L along y for an initial length along y. So y, epsilon, y. What about the stress? The stress is a force along y, and the surface on which I apply it is perpendicular to y also. So it's an sy, so it's a sigma y. Right? So, and you see, so this is where physicists stop and mechanicians start. So physicists would not use indices, right? And they would only work with scalars. But then mechanics people will say that because of these anisotropy and these terms, I cannot have just a scalar to represent the stresses. I need a tensor. I need a matrix, right? So I need to have tensors. So I need to have a stress tensor. So the stress tensor sigma. So I'm going to use these notations. This is a 3x3 matrix where here we'll have sigma xx, sigma xy, sigma xz, and then sigma yy, sigma yz, and then I have a sigma zz, which is here, right? And so the sigma yy that we mentioned here would be the term which is here if I'm doing a tensile stress along the y direction, but I have the same if I'm doing a tensile stress along x or a tensile stress along y. And then here I have shear terms. So we'll say later on why here I called it, sorry, no, it's here, tau, or it could be, actually in this case, it could be a sigma also, but it's a sigma xy. And so the sigma xy would be this guy here. But I could also do a shear applying a force along x, but on a z surface. So that would be a sigma xz, which is this guy, and so on and so on. Yes? In that representation, what is the pressure? so the is it the product? So actually it's so P is so we said P is the stress that we apply on each surface when all these elements here are the same. So a pressure tensor would be something like P, 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 and I have zeros everywhere else. Or minus, because again of this bloody convention, right? So so I have minus P, minus P, minus P. In the case of all three elements are the same, and if they are different, P would be the trace of sigma. And I'm missing two things. It's minus, again, 1/3 times the trace. Yes? So that if all three elements are the same, then this definition here is coherent with that definition and that. Yes? So this is the stress tensor. And so by definition, so sigma ij is the stress which corresponds to applying a force along direction I on a surface which is perpendicular to J. So it means that if I have an elastic body and I look at an elementary surface here which has a surface vector ds, and I apply on this surface a force df, like this, then I have the force df, because of this definition here, is the stress tensor times the vector ds. So I have a vector, I have a 3x3 matrix multiplied by a vector that gives me a vector. And so the stress multiplied by the surface gives me the force applied on that surface. This is clear for everybody? If I have a stress tensor, so if what I do here, for example, I apply a plus sigma in this direction, and I apply a minus sigma in that direction, right? and nothing in the z direction. And in the z direction, it's 0, right? So the trace will be 0. So the pressure is 0. There's no pressure because the pressure has to be of the same sign and on all the different surfaces. So and I can see it here because if here I'm pulling in that direction, so I'm compressing in that direction, but I'm extending in the other direction. Actually, the volume, if I look at the total volume, it's not going to change. So the bulk modulus will not be involved in that deformation. Actually, how is this called? It's called pure shear. So in this case, actually, so if I'm looking at if I'm looking along that direction, if I have initially a square, after deformation, the system will look like this, right? It's extended in one direction, compressed in the other one. If I look at that deformation at 45 degrees, if I tilt my head and I look at that direction, if I look at a point here, it's going to go there. The point here is going to go here. And this is a shear deformation. And I have the equivalent and symmetrical on the other side. I have a displacement here and a displacement there. In that direction, I also have a shear. So actually, it's a bit counterintuitive, but applying a positive stress in one direction and a compressive stress in the perpendicular direction, that gives me a shear deformation with no volume variation. Is that more or less clear? Yes? So now my board is a bit of a mess. We have the pressure, we have the tensile, we have yeah, so there's one last property, which is that the stress tensor it's symmetrical, right? So sigma yx is the same as sigma xy, etc., etc. And this is because of dimensionality. I don't want to get into the calculation, but it's a dimensionality. It's because of the dimensionality of it's related to rotations, and it's related to the moment of inertia. It's a question of dimensionality of the moment of inertia that forces these terms to be equal to those terms. But we don't really need to get into these details. This is clear? So this was for the stress tensor. Now for the deformation tensor. So if I remove all this, so this is for the stresses. Now for the deformations, what happens? So deformations, it's also a tensor. So we're going to have a tensor epsilon, which again, so it's a 3x3 matrix, epsilon xx, again, epsilon yy, epsilon zz, etc., etc. Epsilon xy, epsilon xz, epsilon yz here. And if I'm working in small strains, as we are going to do, how is defined epsilon ij? So one of the terms, so for example, this term or that term, for those who have done elasticity. So if I want to have a definition here, which is consistent with what we have written here, or written there, or written in the tensile deformation that I've erased, I need to define epsilon, no, I don't need to, but I can define epsilon ij as, so it's going to be, yeah, it's going to be related to the gradient of the displacement field. So I'm looking at the displacement in direction j I'm looking at the derivative of the displacement in direction I with respect to the displacement in direction j. And now, so epsilon is also a symmetrical tensor. And so I add the symmetrical part, duj over dxi, and I take 1/2 of this. Why do I add the symmetrical part to the gradient. So this would be the gradient of the displacements. And to define the deformations, I add the symmetrical part. Why do I do that? Again, I'm not going to show it, but it will remove rotations to first order. The one point is that if I take a sample and I just do a rotation, so I don't deform it, I just rotate it, there will be a deformation field associated with the rotation. And so if I only look at the deformation gradient, for a rotation, I will have a non-zero deformation gradient. But rotations are not related to stresses. So I want to remove the rotations. And what we can show, I don't want to do it, but what we can show is that if I take not the deformation gradient, but the symmetrical part of the deformation gradient, then I remove the rotations to first order. So that works only if I'm looking at small strains. So here, this removes rotations at first order, and only first order. So if I look at large strains, then this is not enough. But we're going to only look at small strains. Yes? So sigma is a symmetrical 3x3 matrix. Epsilon is also a symmetrical 3x3 matrix. Now, what happens to Hooke's law? So we had one instance of Hooke's law for the tensile stress, sigma is equal to E epsilon. We have another instance of Hooke's law here with sigma, which is the shear modulus times the strain. We have a third instance here. So if now we're saying that because we can apply different types of deformations, we need to have matrices for the strains and for the stresses, what happens to Hooke's law? So basically, so physically, what does Hooke's law say? What does Hooke's law say? It says that the stresses are proportional to the strains. Just that, right? But now what do I want to say? I want to say that the stress tensor is proportional to the strain tensor. And because everything becomes tensor, it's not really proportional. It means that the stress tensor becomes a linear combination of the strain components, right? So it means that what I want to say is that sigma ij, so any term of that matrix, has to be a linear combination of these terms. So I want to do a sum over these terms. So I will have an epsilon KL. These are the terms of this tensor. And so I need here to have linear components, to have a linear combination of the strains that give me the stress. How many indices do I need here? So here, I need to do a sum over K and L to do a linear combination of these terms. So this C will depend on K and L to have the linear combination. But then I need also an I and a J, because I need to relate, I need one of these linear combinations for each of these guys. So C is actually, it's a fourth order tensor, or it's a 3x3x3x3 matrix. And that's the tensor of elastic constants, right? So this is clear. So this is what sometimes we call, so just Hooke's law or generalized Hooke's law, because now we're talking about tensors, right? So generalized Hooke's law. Okay, and so in terms of matrix notations, we can write that the tensor sigma is this fourth order tensor C. How do you say in French? We say double contracted. Double contracted? So double contracted with epsilon. We said that, in analogy with Hooke's law, in the case of the tensile stress, the energy is, or the energy density is is sigma times epsilon. So here, what happens? What is the energy? What do you think if you want to generalize that? Again with taking in analogy with a spring, we're gonna say that the energy or the energy density So it's not easy, but there will be a 1/2, and then there will be a sum over all the terms Ig of the stress tensor multiplied by the corresponding strain tensor. Yes. So this is so we have the energy here, and we have Hooke's law here. Yes, it works. Is it clear, or am I going too fast? I'm going much faster than what I thought I would do, but it looks like you have already, everybody has already done elasticity or some sort of elasticity, so it's not too fast. You sure? No regret? Okay, I tried. Now you were asking, if I want to specify the elastic properties of a solid, then I need to give this matrix. So how many elements are there in this matrix? The basic one. If it's a 3 by 3 by 3 by 3 matrix. So that's 81 elastic constants. That's an awful lot number of elastic constants. But what? So now we can use symmetries, right? So C has 81 components, but what? So this guy is symmetric. SoCijkl has to be equal to Cjakl, right? So sigma is symmetrical. Sigma symmetric. This implies thatCijkl is equal to Cjikl. Same thing, this guy is symmetrical. So I can also invert, I also haveCijlk, which is Cjikl. Yeah? So that reduces the number of elastic constants to, okay. So you have already done, so yes, 36. How can I show 36 simply? So actually, yes, the stress tensor, because it is symmetrical, actually it has only 1, 2, 3, 4, 5, it has only 6 independent components. So I can use what we call Voigt notations to represent sigma as a vector. And the usual order is sigma xx, sigma yy, sigma zz. So we go down here, and then we go up like this. So we have sigma yz, sigma xz, and then we finish here, sigma xy. So these are the 6 independent components. And now if I write sigma as a vector, then Hooke's law becomes a 6-dimensional vector, which is the product of a 6 by 6 matrix times the 6-dimensional vector of the strains. The only caveat, the thing we have to be careful about, is that, so I try to erase as I no longer need this. Yeah. The only caveat is that if I look at epsilon, because of all the symmetries, the epsilon in this Voigt notation, it's epsilon xx, epsilon yy, epsilon zz, that's fine. For the non-diagonal terms, I have to multiply by 2 to be consistent with this notation, I have a 2 epsilon, sorry, no, it's not xy, it's yz, xz, and 2 epsilon xy. If I add these two here, then I can say that sigma as a vector, so sigma like this, is equal to a 6 by 6 matrix times epsilon like this. And it's because when we are doing the sums here, all of the non-diagonal terms appear twice. So there's the 2 here. And so because of that 2 here, sometimes the 2 times epsilon, people will note them gamma. So that's why here I use the gamma. So this gamma here would be twice the shear deformation. It's a small detail. So here I've added the 2 here. So I have a 6 by 6, and so that's 36 elements. Now I can even reduce these number of independent elements. And why now, what else can I say? Yeah, and how can I see that? So actually, if we go back, I just erased it, but if I look at the energy density, we said this is 1/2 of the sum over I and j of sigma ij epsilon ij. And this I can also, if I use a Hooke's law, I can write it as 1/2 of the sum over ijkl of sigma ijkl epsilon ij epsilon kl. Which means that I can write sigma, write sigma ij as a derivative. Or actually I can write it as a second derivative. Of the energy density here, and I need to divide it by epsilon ij, epsilon kl. But because of Schwarz theorem, I can invert these two. So this is the same as d2f over d epsilon kl epsilon ij. And who is this guy? In terms ofCijkl, this is CKLIJ. So it means that this IJKL, I can switch them, and I get the same term. So for that matrix, what does that mean? It means that this matrix is symmetrical. It's a symmetric matrix. So it's a symmetric 6 by 6 matrix. How many elements are there in a symmetric? 21. So this one is symmetric. And so actually, the largest number of elements is 21. So 21 elastic constants. So elastic constants. That's still an awful lot of elastic constants to compute. But now, what happened? What can I add to that? Now I can add the symmetry of the crystal itself. Because, for example, if I have a cubic system, then for a cubic system, x, y, and z are equivalent. And so that reduces even more the number of elastic constants. What is the most symmetrical solid we can think of? So you have cubic, yeah? You can go one step further. No, hexagonal is less. Simple cubic is less. There's not the threefold symmetry in the simple cubic. Oh no, it's equivalent. Simple cubic is equivalent. Sorry, I said something wrong. Simple cubic is equivalent. Because there's the 3 axis is along the 1, 1, 1. No, but if it's not a crystal, if you look at an amorphous system, so in a crystal, XX is equivalent to YY is equivalent to ZZ. But then this is not equivalent to 1, 1, 1, for example. if I take an amorphous system, then an amorphous system, any direction I'm looking at, statistically is completely equivalent to the other. This is an isotropic solid, right? And you can show, we're not going to do it, but you can show that for an isotropic solid, you only have two independent elastic constants. Now your life is good, right? Only two. So only two. If you have a cubic system, you can show that you have only three independent elastic constants. And then as you remove symmetries, you have more and more independent elastic constants, right? So we have that. And now we add, so plus the symmetries of the solid itself. Okay. So now we go down to two independent elastic constants. Now, as we have said before, I mean, we have seen different elastic constants, right? So when I did the tensile test or the shear or the pressure, I never really talked about the symmetries of the crystal. So actually, implicitly, I was applying an isotropic crystal, but an isotropic solid. So for an isotropic solid, we have already seen different examples of elastic constants. We have seen, first we have talked about E, then we have talked about G, then we have talked about B, then we have talked about nu. So that's more than two already, right? So actually there are different choices of elastic constants, of pair of elastic constants, and there are different ways to write this relation for an isotropic solid. So one way is to say that sigma is equal to E over 1 plus nu, epsilon minus nu over 1 minus 2 nu. If I'm right, I need to check if I'm right. I always, and this is the identity matrix. Let me check. So we're going to go through this again just to make sure, but so this for me is my way to write the identity matrix, right? And so here you see I have sigma, and it's a linear combination of the different terms. But here I have just the matrix epsilon itself, and here I have the trace of the matrix. So this is a linear combination, and I have two elastic constants that are the Young's modulus here and the shear modulus there. The Poisson ratio there, right? So that's one way to write Hooke's law. There's another way with yet other elastic constants, which is lambda trace de epsilon identité plus 2 mu epsilon. And these are two other elastic constants, lambda and mu, that are called the Lamé coefficient. Now, if you have more here, it means that actually G is not, so since we have only two independent, if I say that E and nu are the two independent elastic constants, then there must be a relation between G and E and nu and B and E and nu. To see that, to see the relations, what we do? Well, we apply the cases that we know. So for example, I know that to define B, what do I need to look at? To find B, so to express B, or B will appear if I do a volumetric. So what happens if I do a volumetric deformation? So in that case, what is the stress tensor? We said that the stress tensor will be minus P along the diagonal, right? Minus P, minus P, minus P, and I have zeros everywhere else. What will be epsilon? Yeah, so it's going to be delta Lx over Lx, delta Ly over Ly, delta Lz over Lz, and all three will be, if it's isotropic, all terms will be the same, and they will actually be equal to 1/3 of delta V over V. So 1/3 Yes, that works. And then I have zeros everywhere else. And now I apply Hooke's law. So so I want to apply this. So what is the trace of epsilon? Or I can do it directly. So I have this matrix here, minus p, minus p, minus p, that has to be equal to E over 1 plus nu. And then I have the matrix epsilon. So I have delta v over 3v, and then same, delta v over 3v, delta v over 3v. And then plus nu over 1 minus 2 nu. And then I have trace of epsilon, which is just delta v over v. So delta v over v times the matrix identity. And so you see that only the diagonal terms are non-zero, and they're all the same. So I have a single relation, which is minus p is equal to E over 1 plus nu. And then I have delta v over 3v plus nu over 1 minus 2 nu delta v over v. Right? So I can rewrite that as p is equal to minus, I have something, and then I do the delta v over v. I put it outside, delta v over v. And what remains is E over 1 plus nu. And then I have this guy. So this guy is 1 minus 2 nu plus 3 nu divided by 3 times 1 minus 2 nu. Yes? So that's, and now by identification, what is this guy? This is the bulk modulus. This is B. So I get that B is equal to E, and so this is 1 plus nu, it goes away. So it's E over 3 times 1 minus 2 nu. These are the ones that we use, that everybody uses. But you could all invent your own elastic constants, but in the end, there would be some linear combination of these guys. They cannot be otherwise, because for an isotropic solid, we know that there are only 2 independent elastic constants. So once you have given 2 reference ones, then you know that anything you're going to do will always be a function of these 2. So what you can show is that actually mu here is equal to G. If you take a simple shear, simple shear deformation, and again do the same exercise as we've done here, you're going to show that mu is equal to G, and then lambda is some function of the others. It's not here. Here we have. I've just put. This is, so mu and G is this guy, and then B is that guy. I've forgotten. I don't know by like this the relation between lambda and it's some E over 1 minus nu times 1 plus nu or something like this. Is it clear for everybody? Yes, same thing. Always you take either that relation or that relation. You look at a specific case, and then you identify, and that gives you all the different relations. Clear? So if we go back, what have we covered? So we've looked at these different. That I want to come back to it. So these are the definitions of the stress tensor and deformation tensor, and the fact that they are both symmetrical. Then we have the. So this is a very short summary of everything we've said. I didn't think we'd go into these details, but so this is the general Hooke's law, and then the relation between the different elastic constants, and this is something else. So now yesterday afternoon you've started playing with lamps. Let's say I ask you, what is the bulk modulus predicted by the aluminum potential you used yesterday? How would you do that? So yesterday you have computed the equilibrium lattice parameter, the cohesive energy, the vacancy formation energy. Maybe some of you, I don't know, have had time to look at the interstitial and interstitial formation energy and so on. Now I ask you about elastic constants. So the basic experiment or the basic simulation will be, both of you are correct, but so the basic simulation would be, I take a crystal, FCC crystal at the equilibrium lattice parameter, 4.032, and then what do? Then I change the lattice parameter, make it bigger, make it smaller, and then I look at, so I can look at two things. I can look at how the pressure varies. So I can look at the relation that I've just erased. So I can look at, I know that I have P, which is minus B times delta V over V. So I can constrain, I can change the lattice parameter. So that will change the volume. I measure the pressure. I plot the pressure as a function of this. It should be a straight line. And then I take the slope, and the slope gives me the bulk modulus. That's one way. Another way is I impose a pressure, and then I relax the simulation cell to have this internal pressure. I measure the difference in volume during the relaxation. So I impose the pressure. I measure the relative variation of volume. Again, I plot and I get the slope. I can do something else. That was the other idea. I can also look at the energy, right? And the energy will be some function of delta V over V squared now. It's going to be quadratic. And I look at the curvature, and from the curvature, I can also get the bulk modulus. Right? You agree? You agree? Yeah. In practice, what I found is that looking at the curvature is less accurate than looking at the slope. So I prefer to go directly to that. So with LAMPS, there are two ways. Either you do a succession of simulations, and at every simulation you start with a new crystal and you change the lattice parameter, right? You minimize and you do it again and again and again. Or with LAMPS you can do loops. So what I did is so we start like yesterday. It's a metal atomic style. I start by building an FCC system with 4 unit cells and the equilibrium lattice parameter. Same potential, blah, blah. And then what I do is I do a loop. So I define a variable x, which is of the loop type, and it's going to go from 0 to 20. And then I start a loop. So I will start a loop here, and then I define a pressure, which is just this x value minus 10 in bars. So I'm going to go from minus 10 bar, so minus 1 MPa to 10 bars, so to 1 MPa in 20 steps. And for every pressure, I use this box relax command with the ISO, because I want the cell to remain cubic, and I give as a target the pressure that I have defined just above. So I'm going to do a series of 20 relaxations with the pressure varying from 1 MPa to 10 MPa. And then after the relaxation, I get the pressure as the trace of the matrix, right? So I have the trace of the matrix. I divide by 3 to have the 1/3, and then by 10 to have MPAs. So that's the pressure. I get the lattice parameter as the length of the cell divided by the number of unit cells. And then I get the strain here, which is just, so I want delta V over V. But if delta V is small, delta V over V is just delta Lx over Lx plus delta Ly over Ly plus delta Lz over Lz. But the 3 are the same. So it's 3 times delta Lx over Lx. So I have 3 times. This is delta Lx. So this is the Lx after relaxation minus the reference divided by the reference. So this is 3 times delta Lx over Lx, right? And then I plot this into a file that I call compress.dat. That's fine. You see what I'm doing? And then once I'm here, I do next x and then jump self. So what the program is going to do is from here, it goes by here, and then it does it again and again and again until x is at the last value. That works for everybody? Yeah? And so now we run it. So I run it. It's almost instantaneous for this small cell. And now, oh no, I need to remove, I do it again. And now in this compress file, I have, so this is the strain, this is the stress, or the pressure, and this was just the lattice parameter before I compute the stress. And now I can look at what it gives. So I like to use, for simple things, I like to use a GNU plot, except that it does not work. Sorry. That's, yes. And it's nicely linear, so things are good. And now I need to compute the slope of that curve, and that will give me the bulk modulus. Yes? So then you can use whatever method you want to get the thing. Yesterday I used, again, I used a GNU plot. There's a, I don't know if you ever used GNU plot, but you can do linear and other fits. And if I do the fit, it tells me that the bulk modulus is here. So this is in MPa, so it's 80.1 gigapascals, the bulk modulus, which is what actually we expect. And you can do it for the other, so by applying different types of strains or by imposing different stress tensors, then you can compute the other elastic constants. Yes. Yes, you can impose a shear stress also if you want to. Yeah. That it works? Yeah. Do you have questions, or is it clear? So I forgot to do it, but I'll put that script in the day 2 folder so that if you want to play with it or use it with your own potential, just go for it. That works? Yeah. Yes. We can do that too. Actually, you could do that. That could be an exercise for you if you want to. You take that file and then you change it to apply a strain, and you compute the pressure, and you make sure that you get the same result.
Then the risk is to do that, right? Because we don't know what is the equilibrium constant. So if you take a lattice parameter which is far from equilibrium, you do it.
Sure. Yeah. So the first simulation you have to do is, find your equilibrium lattice parameter. That's the first value, and that's what I need. That's what I use. You need to know what is the equilibrium lattice parameter, and then you do the deformation from that lattice parameter. Yeah. That was, and actually, so it's here. And actually, if you want to compute the strains, the deformations properly, you need to put all the digits behind. Otherwise, your calculations are a bit off. It doesn't change the slope, but the calculations are a bit off. So.
One question. In the equation between bulk modulus and the Poisson's ratio is 0.5.
So Poisson's ratio doesn't need to be 0.5. So for most materials, Poisson ratio is on the order of 0.3. If Poisson ratio is equal to 1/2, it means that the solid is completely incompressible. And if it is completely incompressible, it means that if you apply your pressure, you cannot have a delta V. So in this relation here, if the system is incompressible, if I apply a P here, delta V has to remain 0, so B has to be infinite. And this is what that relation tells you. It also tells you that, so since B has to be positive, mu cannot be more than 1/2 for an isotropic solid. And same thing you have, if you look at the shear modulus. Let me go back to the presentation. The shear modulus depends on on 1 plus nu. And so the shear modulus has to be positive. So nu cannot be less than -1. So nu can be negative, but it cannot be less than -1. Otherwise, your system is mechanically unstable. That works? Are there other questions? No? Yes, Anant?
What motivates volume conservation?
What motivates volume?
Why should materials try to conserve their volume? Is it simply the question of being in equilibrium, or is there something else that is deeper?
I would think that it's, I don't know. I don't know if there's a, a fundamental principle. But I think it's just because of the interactions that you get partial volume compressibility or incompressibility.
Intuitively, you can understand why it's shrinking. But is there something deeper that says, oh, materials inherently would like to preserve their volume?
So actually they do, but only to some extent, right? With the value of the Poisson ratio, and some even expand when you pull on them. So you can have, but there, I don't know. I don't know any deep reason for that. Yeah. Sure. Yeah. And thanks for the question, but yeah, I have no good answer to give you either. So actually, so that tells you that there is an equilibrium lattice parameter. It does not tell you if the system is incompressible or not. Actually, it depends on how the bonds are organized. So for example, if you take the crystal that does not exist, so if you take a simple cubic crystal like this, and if you pull on it, so what's the Poisson ratio of a simple cubic crystal like this one? Yes, so the Poisson ratio is, it's 0, right? Now, if I add, so but I know that this system, if I shear it, it's going to be unstable. But if I want to stabilize it, I can add springs along the diagonals. Then what happens if I pull on it? Yes, and so you're going to have a lateral contraction. So there's a finite Poisson ratio. You can do the calculation. I forgot what the value is, but there's a definite non-zero Poisson ratio for that system. But that depends on how that depends on the springs that I have added along the diagonals, right? So the value of the Poisson ratio depends on how the bonds are organized, and you can have different types of. So I have 2 minutes. As a French person, there's a very good there's a well-known example of a system with a 0 Poisson ratio. Do you know what it is? Cork. And you know why it's so important for France? Because you have your wine bottle, and if you use a cork which is made of a material with a positive Poisson ratio, you press on it, what is it going to happen? So you press on your, on the, sorry, how do you call it? The cork, the thing, the cork. You try to, so you want to put the cork in to shut the bottle. If the Poisson ratio is positive, what is it going to happen when you try to put it in? It's going to expand, and so you're not going to be able to put it in. If it's oxetic, you press on it. What is going to happen if your cork is oxetic? If the Poisson ratio is negative, you try to put it in, it's going to contract, it falls into the void. No, you cannot do that. And so cork is magic because it has a 0 Poisson ratio, or very, very close to 0 for a Poisson ratio. So when you press on it to put it into the bottle, it does not expand nor contract. And so it stays, and it allows you to put it in and still seal the wine bottle. Very important for French people. Very, very important. Do you have other questions, or no? Everything is good. Okay. So now the last thing I want to talk about is mechanical equilibrium. So for now, we're going to forget about that. And so actually for the elastic constants, in lamps, we haven't talked about that, but there's so at least you can access it if you are using Linux or Mac. There's a folder called example. And in that folder, there's one of the example, which is called elastic constant or something. There's a script. You run the script, and it gives you all the elastic constants. It computes everything. All the matrix is computed with this script. So, and it applies strains and measures stresses, and then does a fit and gives you the elastic constants. And it works very well. Sorry, no, one thing to add. It works very well, but so what it does is it starts from the equilibrium lattice constant, and then it does one expansion in one direction and one contraction in the other direction. But there's a finite step that you have to give to do the finite expansion or contraction. We have come across machine learning potentials that did not give you the correct value if that step, the default step, is too small for some of the machine learning potentials. We had to increase the size of the step to get the right values. There are some tricky things with some of the machine learning potentials that have some very small nonlinearities at the beginning of the potential. So we ran into trouble some years ago with this. Anyway, okay, detail. So now mechanical equilibrium. Let's assume that I have a big elastic solid. So this is my elastic solid. And now let's assume, let's inside that solid, by thought, I'm going to isolate a smaller volume that I call V. And the volume is limited by a surface that I will call S. And there is a normal vector along that surface that we can call n here. Okay, which is the outgoing normal vector to that volume that I've decided. I say it's an arbitrary volume that I've decided to isolate by my mind in that elastic body. Okay, you see what I'm doing? Now, if I am looking at an elementary surface S here, so with a normal surface vector S, what is the force applied on that elementary surface by the rest of the elastic body? By definition of something we just talked about, it's the stress tensor times ds, right? So the force, the elementary force on that small surface here will be the stress tensor at that position times ds. So if I want to know what is the total force applied on that volume, I integrate, right? So f tot will be the integral over the surface of sigma times ds. Now, as a, I don't know if in mechanics you see it. No, yes, you see it in mechanics also. When you see a surface integral like this, what you want to use the divergence theorem, right? But usually, so usually what you have is integral of some vector times ds over the surface, and you say with the divergence theorem that this is equal to the integral over the volume of the divergence of the vector times dv. Here it's a bit different because this is not a vector, it's a matrix, but actually it works the same. So we have an equivalent of a divergence of a matrix, and you can show that the same math applies. And this is equal to the integral over the volume of the divergence of the matrix sigma times dv. Now, this is a vector. Sorry. This is a vector, so divergence of sigma is a vector. And if I look at the eth component of that vector, this is the divergence of the eth line of that matrix. So this is the sum over j of d sigma ij over dxj. If I have a vector f, the divergence of the vector, it's the sum of the derivative of what am I doing? Yes, it's the sum of the derivative of the jth component of f by xj. So here I'm doing the same. I'm doing a sum over j of sigma j here divided by xj, but I do this for every line. So this is the divergence of the eth line of the tensor. Is that clear? Because so the divergence of a vector is a scalar. The divergence of a vector is a the divergence of a tensor of a 2x2 tensor is a vector. So it's not a dot product. It's just a multiplication. This is a scalar, and this is a vector. So this is just a multiplication. Does that work? And left-hand side is a force. Yes. So this is a vector. This is a matrix times a vector, so that's a vector. And this is a vector times a scalar, so it's a vector. Yes, that works for everybody? Yeah? Okay, now assume that we also have, as we usually do, assume that we also have gravity. So there's a volumic force inside the volume, which would be the density of the solid multiplied by the gravity, by g, right? So the total force, if I include that, the total force on the system, on that volume here, on that volume V here, will be divergence of sigma plus rho g, the whole thing times dv. Is that clear? Yes? So now, if I am at mechanical equilibrium, what happens? By definition, if I am at equilibrium, the total force on that volume has to be 0. This is equal to 0 at equilibrium. But now, so what have I done? I've said that I take an arbitrary volume, and the force on that volume has to be 0. But so I've taken that volume, but I could have taken that volume, or that one, or that one, or something which is very close to this one, but just a little difference here and then back here. Every time, the integral has to be 0. What does that mean? It means that the function itself has to be 0. Otherwise, if somewhere it is non-zero, then I can just, if here, for example, the function is non-zero, if I take v around that value, then the force will be non-zero. But it is 0 everywhere. So that means that divergence of sigma plus rho g is itself equal to 0 everywhere in the solid. That's the equilibrium equation for the solid, right? So I have this equation. So this is in terms of stress tensor. But now what I can do is I have so divergence of sigma plus rho g is equal to 0. By the way, this equilibrium expression here is very general. As soon as you can define a stress tensor, then this applies. So it doesn't need to be linear elastic, for example. Any solid where you can define a stress tensor will follow this rule. So this is a very general equilibrium equation, right? But now if we look at a linear elastic isotropic solid, we have this relation. We also have the fact that sigma is equal to 1 over plus mu epsilon plus mu 1 minus 2 nu trace of epsilon identity. And then we also have the fact that epsilon ij is 1/2 of dui over dxj plus duj over dxi. So you start from here, you replace sigma by this, you suffer through the calculations, then once you're done here, you replace epsilon by this, you do some more calculations, and at the end of the day, you can get what is the equilibrium equation in terms of the displacement field. And that's called the Navier equation, and it's given here. So what you find at the end of the day, so here there's a lot of time that you spend doing some math, and you get E over 2 multiplied by 1 plus mu, and then you have Laplacian of u plus 1 over 1 minus 2 mu, and then you have the grad of the divergence of u, plus if you have a volumic force, you have rho g, and the whole thing is equal to 0. Yes? You see how you get there, right? So this is the equilibrium equation for a linear isotropic elastic solid. It's a differential equation. So to solve it, you need this equation. And what do you need also? You need boundary conditions that can be either imposed displacements or imposed forces or stresses on the outside of your body. With the boundary conditions and this equation, you can get what is the equilibrium displacement field in your solid. And then you can backtrack, actually. If you know the displacement, you know the strain, then you know the stress, and you know everything. That works? Yes? So I'm almost at the end. What did I want to say? What's very particular about this equation? Who has done fluid mechanics among you? Oh, one only. Ah, okay. So no one knows what Navier-Stokes equation is. Okay, sorry guys. I was trying. How can I? Okay, let's assume that I know two solutions of that equation. I can solve for that equation and assume that I can solve it and find two solutions, U1 and U2. What happens to U1 plus U2? It's also a solution. So this equation is linear, right? The Laplacian, the Laplacian of a sum is the sum of the Laplacian, and then all of these operators are also linear. So it's a linear equation. So if I know two solutions, then the sum of the two solutions is also a solution. So that means that I can use what we call the superposition theorem. I can decompose my global problem into smaller problems, and then I sum the solutions, and that gives me the overall solution. That's the superposition theorem. That's what I said here. Then I'm not going to do it. It's too late, and it's mathematically involved. It's just that when you have a linear solution like this, there are two things you can do that can really be super helpful. One is you can use what we call Green's function, which is that if you know the solution of that equation for an elementary problem, which is, for example, here, I assume that the force is equal to 1 in one direction, 0 everywhere else, and only on one point in space. If I know the solution of that equation for that elementary force, then I know the solution for any force distribution, because the force distribution is just the sum of elementary forces like this. So the solution for the force distribution will be the sum of the elementary forces. So, and the solution of that problem is called the Green's function. So that's one thing I can do. If I have something linear, there's something else I can do mathematically, a mathematical transformation that I can do. I can take the Fourier of that equation, and I can solve elasticity in Fourier space. And actually, in Fourier space, your life is very simple, much simpler than in real space. And that's what I just wanted to mention here. You have a direct matrix solution for your elasticity equation in terms of the Fourier transform of the Green's function.